In this unit, we shall learn the applications of matrices and determinants. Matrix is a set of real numbers arranged in rows and columns within two parentheses. To define the inverse of a matrix, we must first understand the concept of adjoint of a matrix. Adjoint. Let Aij be a square matrix of order n. Let A of ij be the cofactor of Aij. Then the nth order matrix Aij is called the adjoint of A and is denoted by adjoint of A. The adjoint A is nothing but the transpose of the cofactor matrix Aij of A. Theorem. Let us prove this result for a square matrix A of order 3. Follow the steps shown on the screen. In general, we can prove that A adjoint of A is equal to modulus of A into In is equal to adjoint of A. Let us consider the given matrix as A. Before we find the adjoint given matrix, we first find the cofactors of all the 9 elements and then arrange it in the proper order. The cofactor of matrix A is determined as shown above. From the above, the adjoint of A is the transpose of the cofactor. Inverse. Let us consider a square matrix A. Matrix B is said to be the inverse of A if it satisfies the condition AB is equal to BA is equal to identity matrix I. The inverse of matrix is unique. Next, let's find a formula for computing the inverse of a matrix. From this equation, it is clear that the inverse of A is nothing but 1 by modulus of A into the adjoint of A. We denote this by A inverse. Thus, we have the following formula for computing the inverse of a matrix through its adjoint. If A is a non-singular matrix, there exists an inverse which is given by A inverse is equal to 1 by modulus of A into adjoint of A. Properties. If A and B are any two non-singular matrices of the same order, then AB is also non-singular. That is, the inverse of product is the product of the inverse taken in the reverse order. Proof is shown above. 2. Reversal law for transposes. If A and B are matrices conformable to multiplication, then AB transpose is equal to B transpose A transpose. That is, the transpose of the product is the product of transposes taken in reverse order. 3. For any non-singular matrix, A transpose inverse is equal to A inverse transpose. The proof is shown on the screen. Computation of inverse. The following examples illustrate the method of computing the inverse of the given matrices. 1. In example 1, the determinant value of A is 2, which is not equal to 0. A is a non-singular matrix. Hence, it is invertible. A matrix formed by the cofactors with adjoint is the transpose of the cofactors. Therefore, A inverse is 1 by modulus of A into adjoint of A, as shown above. In the above example, the determinant of A is equal to -1, not equal to 0, and the determinant of B is equal to 1, not equal to 0. So, A and B are invertible. Modulus AB is equal to -1, not equal to 0. Therefore, AB is also invertible and AB inverse is equal to 1 modulus of AB into adjoint of AB is equal to B inverse A inverse. From equation 1 and 2, we have AB inverse is equal to B inverse into A inverse. Solution of a system of linear equations by matrix inversion method. Consider a system of n linear non-homogeneous equations in n unknowns, x1, x2, x3, and so on up to xn, as shown above. We get the matrix equation Ax is equal to B, where the matrix A, X, and B will be as shown on the screen. If the coefficient matrix A is singular, then A inverse exists. Pre-multiply both sides of equation 1 by A inverse, we get A inverse Ax is equal to A inverse B, A inverse A, X is equal to A inverse B. X is equal to A inverse B is the solution of 1. Thus, to determine the solution vector X, we must compute A inverse. For the above example, the given system of equations can be written in the form of Ax is equal to B. Since A is non-singular, A inverse exists. The inverse of A is shown above. The solution is given by X is equal to A inverse B. Therefore, X is equal to 1, Y is equal to 2, Z is equal to 3. Rank of matrix. Rank is a non-negative integer which can be associated with each matrix. A matrix obtained by leaving some rows and columns from the matrix A is called a submatrix of A. In particular, A itself is a submatrix of A because it is obtained from A by leaving no rows or columns. The determinant of any square submatrix of the given matrix A is called a minor of A. If the square submatrix is order R, then the minor is also said to be order R. Definition. The matrix A is said to be of rank R if A has at least one minor of order R which does not vanish. Every minor of A of order R plus 1 and higher order vanishes. In other words, the rank of a matrix is the order of any highest order non-vanishing minor of the matrix. The rank of A is denoted by the symbol shown. The rank of a null matrix is defined to be 0. The rank of the matrix A is second order matrix. Therefore, the highest order of minor of A is also 2. The minor is given as shown above, that is, equal to 9 not equal to 0. The highest order of non-vanishing minor of A is 2. Hence, rank of A is equal to 2. Elementary transformations on a matrix. Interchange of any two rows or columns. Multiplication of each element row or column by any non-zero scalar. Addition to the elements of any row or columns, the same scalar multiples of corresponding elements of any other row. The above elementary transformations taken in order can be represented by means of symbols as shown. The matrix A is equivalent to the matrix B, symbolically denoted by A is equal to B. Two matrices A and B of the same order are said to be equivalent. Equivalent matrices have the same rank, echelon form of a matrix. A matrix A of order m by n is said to be in echelon form if every row of A which has all its entries 0 occurs below every row which has a non-zero entry. The first non-zero entry in each non-zero element in a row is 1. The number of zeros before the first non-zero element in a row is less than the number of such zeros in the next row. By elementary operations, one can easily bring the given matrix of non-zero echelon form. In the following examples, we illustrate the method of finding the rank of matrices by reducing them to the echelon form. The given matrix can be written as triangular or echelon form using suitable rule. The last equivalent matrix is in echelon form. The number of non-zero rows is 2. Therefore, rank of A is equal to 2. The geometry of solution sets. The solution set of a system of linear equations is the intersection of the solution sets of the individual equations. That is, any solutions of a system must be a solution of each of the equations in that system. The equation Ax is equal to B, A not equal to 0 has only one solution, namely x is equal to B by A, and it represents a point on the line. Similarly, a single linear equation in the unknown has a line in the plane as its solution set, and a single linear equation in three unknowns has a plane in space as its solution set. Illustration 1. Consider the solution of the following three different problems. 1. 2x is equal to 10. 2. 2x plus y is equal to 10. And 3. 2x plus y minus z is equal to 10. Solution. First one. 2x is equal to 10. X is equal to 5. We have to determine the values of two unknowns from a single equation. To find the solution, we can assign arbitrary value to x and solve for y, or choose an arbitrary value to y and solve for x. Suppose we assign x an arbitrary value k. We obtain x is equal to k and y is equal to 10 minus 2k. This formula gives the solution set in terms of parameter k. For example, when k is equal to 1, 2, 5, minus 3, 1 by 2, we get 1, 8, 2, 6, 5, 0, minus 3, 16, and minus 1 by 2, 9 as the respective solutions. Second, 2x plus y minus z is equal to 10. In this case, we have to determine three unknowns x, y, and z from a single equation. We can assign arbitrary values to any two variables and solve for the third value. We assign arbitrary value s and t to x and y respectively and solve for z. We get x is equal to s, y is equal to t, and z is equal to 2s plus t minus 10 is the solution set. For different values of s and t, we get different solutions. Cramer's rule method, determinant method. Cramer's theorem provides a useful formula for the solution of certain linear system of an equation in n unknowns. This formula is useful for studying the mathematical properties of a solution without actually solving the system. Theorem, Cramer's rule. If Ax is equal to b is a system of n linear equations in n unknowns such that determinant of A not equal to 0, then the system has a solution. This solution is x1 is equal to determinant of A1 by determinant of A, x2 is equal to determinant of A2 by determinant of A up to xn is equal to determinant of an by determinant of A, where Aj is the matrix obtained by replacing the entries in the jth column. Cramer's rule for non-homogeneous equations of two unknowns. Let us start with the system of two linear equations in two unknowns x and y. A11x plus A12y is equal to B1. A21x plus A22y is equal to B2. Delta x, delta y are the determinants which can also be obtained by replacing first and second column respectively by the column of constants containing B1 and B2. That is, since delta x, delta y are unique, there exists a unique solution for the above system of equations. The method stated above to solve the system of equation known as Cramer's rule. Cramer's rule is applicable when delta is not equal to 0. If delta is equal to 0, then the given system may be consistent or inconsistent. Case 1. If delta is equal to 0, delta x is equal to 0, delta y is equal to 0, and at least one of the coefficients a11, a12, a21, a22 is non-zero, then the system is consistent and has infinitely many solutions. Case 2. If delta is equal to 0 and at least one of the values delta x, delta y is non-zero, then the system is inconsistent. That is, it has no solution. To illustrate the possibilities can occur involving systems of linear equations with two unknowns, consider the following example. Delta is equal to 0, delta x is equal to 0, delta y is equal to 0, and at least one of a11, a12, a21, a22 is non-zero. It has infinitely, case 1, many solutions. The above system is reduced to a single equation x plus y is equal to 3. To solve this equation, assign y is equal to k. Therefore, x is equal to 3 minus 2y is equal to 3 minus 2k. The solution is x is equal to 3 minus 2k, y is equal to a. K belongs to R. For different value of k, we get different solution. In particular, 1, 1, minus 1, 2, 5, minus 1, and 8, minus 2.5 are some solutions for k is equal to 1, 2, minus 1, and minus 2.5 respectively. Non-homogeneous equations of three unknowns. Consider the system of linear equations. a11x plus a12y plus a13z is equal to b1. a21x plus a22y plus a23z is equal to b2. a31x plus a32y plus a33z is equal to b3. Let us define delta x, delta y, and delta z is already defined for two unknowns. As we discussed earlier, for two variables, we give the following rule for testing the consistency of the above system. Case 1. If delta not equal to 0, then the system is consistent and has a unique solution. Using Cramer's rule can solve this system. Case 2. If delta is equal to 0, we have three important possibilities. Subcase 2a. If delta is equal to 0 and delta x is equal to delta y is equal to delta z is equal to 0, and at least one of the 2 by 2 minor of delta is non-zero, then the system is consistent and has infinitely many solutions. In this case, the system of three equations is reduced to two equations. It can be solved by taking two suitable equations and assigning an arbitrary value to one of the three unknowns and then solve for the other two unknowns. Subcase 2c. If delta is equal to 0 and delta x is equal to delta y is equal to delta z is equal to 0 and all their 2 by 2 minors are 0, at least one of the elements of delta is non-zero, Aij not equal to 0, then the system is consistent and it has infinitely many solutions. In this case, system is reduced to a single equation. To solve, we can assign arbitrary values to any two variables and can determine the value of a variable. Subcase 2d. If delta is equal to 0, delta x is equal to delta y is equal to delta z is equal to 0, or 2 by 2 minus delta is equal to 0, and at least one 2 by 2 minor of delta x or delta y or delta z is non-zero, then the system is inconsistent. Theorem: if a non-homogeneous system of linear equations with more number of unknowns than the number of equations is consistent, then it has infinitely many solutions. To illustrate the different possibilities when we solve the above type of system of equations, consider the following examples. Solution 1. 2x plus y plus z is equal to 5. X plus y plus z is equal to 4. X minus y plus 2z is equal to 1. We have delta not equal to 0. The system has unique solution. By Cramer's rule, x is equal to delta x by delta is equal to 3 by 3 is equal to 1. Y is equal to delta y by delta is equal to 6 by 3 is equal to 2. Z is equal to delta z by delta is equal to 1. Therefore, the solution is x is equal to 1, y is equal to 2, z is equal to 1. X, y, z is equal to 1, 2, 1. Solve the following system of linear equation by determinant method. 1. X plus y is equal to 3. 2x plus 3y is equal to 7. Solution 1. X plus y is equal to 3. 2x plus 3y is equal to 7. From the above, delta is equal to 1. Delta x is equal to 2. Delta y is equal to 1. Therefore, by Cramer's rule, x is equal to delta x by delta is equal to 2 by 1 is equal to 2. y is equal to delta y by delta is equal to 1 by 1 is equal to 1. Solution is x, y is equal to 2, 1. Solve the following non-homogeneous equation of three unknowns. Solution 1. Delta is equal to 15, delta x is equal to 15, delta y is equal to 30, delta z is equal to 30. By Cramer's rule, x is equal to delta x by delta is equal to 1, y is equal to delta y by delta is equal to 2, z is equal to delta z by delta is equal to 2. Solution. Let x, y and z be the number of coins respectively in each category rupee 1, rupees 2 and rupees 5. From the given information, x plus y plus z is equal to 30 is equation 1. X plus 2y plus 5z is equal to 100 is equation 2. Here we have three unknowns but two equations. We assign arbitrary values k to z and solve for x and y. The solution is x minus 3k minus 40, y is equal to 70 minus 4k and z is equal to k. Homogeneous linear equation. A system of linear system is said to be homogeneous if the constant terms are all zero. That is, the system has the form as shown. Every homogeneous system of linear equation is always consistent, since all such systems have x1 is equal to 0, x2 is equal to 0, up to xn is equal to 0 as a solution. This solution is called trivial solution. If there are other solutions, they are called non-trivial solutions. Because a homogeneous system always has trivial solutions, there are only two possibilities. 1. The system has only the trivial solution. 2. The system has infinitely many solutions in addition to the trivial solution. As an illustration, consider a homogeneous linear system of two equations in two unknowns. X plus y is equal to 0 and x minus y is equal to 0. The graph of these equations are lines through the origin and the trivial solution corresponding to the point of intersection at the origin. For the following system, x minus y is equal to 0 and 2x minus 2y is equal to 0. The graph shows that the system has infinitely many solutions. There is one case in which a homogeneous system is assured of having non-trivial solutions, namely, whenever the system involves more number of knowns than the number of equations. A homogeneous system of linear equations with more number of unknowns than the number of equations has infinitely many solutions. Solve. X plus y plus 2z is equal to 0. 2x plus y minus z is equal to 0. 2x plus 2y plus z is equal to 0. Solution. Here, delta not equal to 0. The system has unique solution. The above system of homogeneous equation has only trivial solutions. Say x, y, z is equal to 0, 0, 0. Solve. X plus y plus 2z is equal to 0. 3x plus 2y plus z is equal to 0. 2x plus y minus z is equal to 0. Solution. Since delta is equal to 0, it has infinitely many solutions. At least 2 by 2 minus of delta not equal to 0. The system is used to two equations, assigning arbitrary value to one of the unknowns, say z is equal to k, and taking first and last equations, x plus y is equal to minus 2k, 2x plus y is equal to k. By using Cramer's rule and solving it, the solution is x is equal to 3k, y equal to minus 5k, z is equal to k. Rank method. Let us consider a system of m linear algebraic equation in n unknown x1, x2, x3 up to xn. The equations can be written in the form of matrix equation as Ax is equal to b, where the m by n matrix A is called the coefficient matrix. A set of values x1, x2, x3 up to xn which satisfy the above system of equations is called a solution of the system. The system of equations is said to be consistent if it has at least one solution. A consistent system may have one or infinite number of solutions. When the system possesses only one solution, then it is called a unique solution. The system of equations is said to be inconsistent if it has no solution. The mx into n plus 1 matrix is called the augmented matrix of the system, and it is denoted by A, B. The condition for the consistency of a system of simultaneous linear equations can be given in terms of the coefficient and augmented matrices. The system of simultaneous linear equations Ax is equal to B is consistent if and only if the matrices A and A, B are of the same rank. Steps to be followed for testing consistency. Write down the given system of equations in the form of a metric equation Ax is equal to B. Find the augmented matrix A, B of the system of equations. Find rank of A and rank of A, B by applying only elementary row operations. Column operations should not be applied. If the rank of A is not equal to rank of A, B, then the system is inconsistent and has no solution. If the rank of A is equal to rank of A, B is equal to n, where n is the number of unknowns in the system, then A is a non-singular matrix and the system is consistent and it has a unique solution. If the rank of A is equal to rank of A, B is lesser than n, then also the system is consistent but has an infinite number of solutions. Examine the consistency of the equations. The augmented matrix A, B is shown above. Bring out using suitable rule in the form of echelon form or triangular form. The last equivalent matrix is the echelon form. It has 3 non-zero rows. Therefore, rank A is equal to rank of A, B is equal to 3. That is equal to the number of unknowns. The given system is consistent and has unique solution. To find the solution, we see that the given system is equivalent to the matrix equations and then so on. We get x is equal to 1, y is equal to 3 and z is equal to 5. Investigate for what values of lambda, mu, the simultaneous equation x plus y plus z is equal to 6, x plus 2y plus 3z is equal to 10, x plus 2y plus lambda z is equal to mu have 1. No solution, 2. A unique solution, and 3. An infinite number of solutions. The matrix equations corresponding to the given system is equal to Ax is equal to B. Case 1. Lambda minus 3 is equal to 0 and mu minus 10 not equal to 0. Case 2. Lambda not equal to 3 and mu can take value in R. Therefore, rank of A is equal to 3, rank of A, B is equal to 3 and both are equal. That is equal to 3 unknowns. Therefore, the given system is consistent and has a unique solution. Case 3. Lambda minus 3 is equal to 0 and mu minus 10 is equal to 0. That is, lambda is equal to 3 and mu is equal to 10. Therefore, rank of A is equal to rank of A, B is equal to 2, less than the number of 3 unknowns, and the given system is consistent but has an infinite number of solutions. Homogeneous linear equations. A system of homogeneous linear equations is given by am1x1 plus amx2 plus am3x3 up to plus amnxn is equal to 0. Since rank of A is equal to rank of A, 0 is always true, we see that the system of homogeneous equations is always consistent. Note that x is equal to 0, x1 is equal to 0, x2 is equal to 0, up to xn equal to 0 is always a solution of the system. This solution is called a trivial solution. If the rank of A is equal to rank of A, B lesser than n, then the system has a non-trivial solution. If rank of A is equal to n, then the system has only trivial solution. Solve the following homogeneous linear equations. X plus 2y minus 5z is equal to 0. 3x plus 4y plus 6z is equal to 0. X plus y plus z is equal to 0. The given system of equations can be written in the form of matrix equation Ax is equal to B. Using suitable rule and bringing out in the form of echelon, clearly rank of A, B is equal to 3 and rank of A is also 3 because all the 3 rows are non-zero rows. Therefore, the given system is consistent and the unique solution is trivial solution. Therefore, x is equal to 0, y is equal to 0 and z equal to 0.
Find the adjoint of the following matrices: 3 minus 1, 2 minus 4. Find the adjoint of the following matrices: 2, 5, 3, 3, 1, 2, 1, 2, 1. Find the adjoint of the matrix A is equal to 1, 2, 3, minus 5 and verify the result. A into adjoint of A is equal to adjoint of A is equal to mod of A. Find the inverse of each of the following matrices: 1, 0, 3, 2, 1, minus 1, 1, minus 1, 1. Find the inverse of each of the following matrices: 2, 2, 1, 1, 3, 1, 1, 2, 2. If A is equal to the matrix of 1, 2, minus 3, 1 and B is equal to the matrix of 2, minus 1, minus 1, 1, verify that AB inverse is equal to B inverse A inverse. AB transpose is equal to B transpose into A transpose. Show that the adjoint of A is equal to the matrix of 1 minus 2 minus 2, 2, 1 minus 2, 2 minus 2, 1 is 3A transpose. A is equal to 1 by 3, the matrix of 2, 2, 1, minus 2, 1, 2, 1 minus 2, 2. Prove that A inverse is equal to A transpose.